Hello everyone, my name is Milad. I'm a PhD candidate from Simon Fraser University from Canada. Today I'm going to talk about a part of my PhD studies which is titled A New Nonlinear Micromechanical Structure used in a MEMS inertial sensor. So MEMS accelerometer have been developed in recent years and used in different kinds of applications such as navigation, structural monitoring, and specifically in seismic and gravity measurement. Regarding the seismic and gravity measurement applications, I can mention geophysical studies or source explorations. So this picture shows an example of application of a gravimetry in geophysics. So you can see that the drop in lava level actually shows that a drop signal in the gravity signal, shows a drop in a gravity signals. There are two kinds of traditional gravimeters, absolute gravimeters and the relative ones. Absolute gravimeters actually measure the absolute value of the gravity used as a reference, and they are so bulky and expensive. On the other hand, relative gravimeters measure the gravity change, and they are based on the mass spring systems, and compared to the absolute ones, they are much smaller and portable. Traditional gravimeters are so bulky and expensive, and they can be replaced by MEMS sensors. And especially for the relative gravimeters. They are so compact, the MEMS gravimeters are so compact, they consume low power, and they take advantage of mass producibility. The accelerometers actually work, MEMS accelerometer work based on the mass spring systems, and one of the most important parameter in an accelerometer is the mechanical sensitivity. So to improve this parameter, one can increase the mass of the proof mass or decrease the stiffness. Or we can say that it's inversely proportional to the natural frequency. So to improve the sensitivity, one solution is increase in proof mass size, which is limited by the chip area in terms of microfabrications, or reducing the spring constant or just drop in a stiffness of a spring. So in terms of linear springs, they should be long narrow beams enough to just decrease the stiffness, which makes them fragile and vulnerable. Also, they have a large initial displacement to just get the set point, and also they have a low resolutions. It means that there's difficult to detect a very small change in a large domain. So nonlinear spring can be a solution to get a near zero spring constant by introducing a negative springs. So regarding the developed MEMS gravimeters, we can categorize them to two types, linear springs and nonlinear springs. So the linear springs actually, as you can see here, have a high length and with a narrow width. So the ratio would be so high. And also you can see that they use large proof mass to get to the 1G and detect the signals. And also you can see another kind of developed sensor is based on the resonance sensing. It has a very high resonance frequency, and the beam size, again, actually is too high. So the nonlinear springs, actually, most of them based on the curve-shaped beams, but still the beam size, the ratio of the length to the width is so high, and the proof mass size still large. So the existing challenges actually is the large preload and initial displacement required to activate the nonlinearity of these two devices, which means that to just soften the springs, we have to just apply a large force. So the large chip area, large proof mass is needed, and the long, narrow beams make the devices fragile and vulnerable. So we came up with an idea for the nonlinear spring systems. As you can see here, we have a proof mass and two horizontal springs, which are connected with the solid links, which actually is initially tilted about 2 degrees or 3 degrees. And we have a joint connections between the solid links and proof mass, and also between the solid links and the horizontal springs. So as the proof mass pulled down by the inertial force of the proof mass, these two horizontal springs actually pushed against the wall, and some energy stores in these two, and a horizontal force actually applying horizontally in these two solid links. So as it just move further and move down a little bit, you can see that a part of this force actually applied in a y direction, and it can cancel out the part of force which come from the down springs or from the linear springs, and just introduce a negative stiffness, and finally get a near zero springs. So this idea actually is designed based on the microfabrication rules. So we have two beams at the left side, which act as a linear spring here, a horizontal spring here, and these two beams actually act as a hinge joint for this point. So this is a finite element analysis, which shows that if we can get a negative spring as it just moved. This is the linear area, and if we just pass the turning point, you can see that the system shows a negative stiffness and can just produce zero stiffness along with the linear one at the bottom. So we embedded these two nonlinear structures symmetric in a MEMS sensor. This is a device layer. The top one is a device layer, and all the features are patterned in the device layer. And also we have a handle layer at the bottom. And also these two nonlinear structure actually working with two symmetric folded beams to suspend the proof mass. So this animation actually shows the nonlinear behavior of the system at a certain point. So as you can see, after a certain point, you can see that the proof mass drop, and the nonlinear push the proof mass down to get a near zero spring, near zero stiffness. So regarding the fabrication, we sketch the layout. We start with sketching the layout, and then we pattern the layout on a SOI wafers, and etch the SOI with a deep reactive ion etching, and finally each chip's actually released by VHF. So this is the final dimension of each chip, and the final devices is packaged and wire bonding to a ceramic here for testing. So this is two pictures, two SCM pictures of our devices. This is the nonlinear beams, a part of nonlinear beams, and the other one is a cross sections of the electrodes. And also we integrated the device with two sets of combs at the top and bottom to measure the displacement differentially. So this is our readout circuit for measuring the displacement and testing the device. So you can see the combs here at the top and the bottom of the devices, and we use a TIA to just measure the output voltage and sense the displacement. So the output voltage actually proportional to the delta C, and it's proportional to the displacement of the proof mass, and finally can sense any variation in G. So this picture shows the experimental setup that we use. The MEMS device actually is fixed on this tilt stage. It's very accurate tilt stage that we can just tilt with a high accuracy, about 10 microdegree. So this is the comparison between the finite element and experimental. As you can see here, At the beginning, the system shows a linear behavior to a certain point, and after that, you can see that the negative spring activate and shows a decrease in a K. So this is where we have a just negative spring at the top. So, and after that, the system still shows the linear behavior. So, and also this figure shows the drop in a K or stiffness as we just pull down the proof mass. So the other test is the resonance measurements. So we have we actually test the device to get a resonance frequency. The sensor is just located in the chamber and in a vacuum conditions. So you can see that the minimum resonance frequency that we can get is about 16 hertz. And also as we tilted the sensor, the resonance would be changed. That shows that actually this is the minimum resonance that we could get. So as we tilt it, the resonance would change, and the minimum one would be about 16. And also, it should be noted that the resonance frequency in a horizontal position is about 127 hertz. This is a comparison table between our work and the similar other works. So you can see that the proof mass size drop, and also the preload required is much less than the others, and the proof mass still just smaller than the other one. And this is the final one is the bandwidth of each sensor. Regarding the conclusion, we come up with a new design for a nonlinear spring, and it's implemented in the MEMS sensor to investigate the behavior. Device design is robust and easy to adapt to the different applications. A prototype was fabricated and experimental result to just compare with the model. The design shows good promise for application where softening spring design may be needed. And regarding the future work, we have to optimize the nonlinear spring characteristics to fit a linear model to the nonlinear area and just detect any change in a G. And finally, set up a compact package for controlling temperature and pressure to do a long-term measurement for the gravity signals. Thank you for your listening.